Our first presenter will be Amirkhanian, and he will be speaking on fiber reinforced overlays.
Alrighty, thank you. So I come all the way from nice warm weather in Alabama. A few days ago I was wearing shorts because it was 70 degrees and sunny, and then the plane lands here and it's like a blizzard, so that was fun. But today I'll talk about fiber reinforced overlays. Not necessarily composite pavements that we heard about, but actual overlays. And first, need to thank the co-authors of this report that is going to be coming out in the next couple of weeks, I believe. Dr. Jeff Raisler, Dr. Amanda Bordelon, Dr. Alex Brand, and then Jared Gross and John Cunningham from Snyder & Associates. And this project was funded and supported by the CP Tech Center at Iowa State and the National Concrete Consortium. So we developed two technical documents, one huge one that covers fiber reinforced overlays for pavements, and then a much smaller one that looks at the current state of practice of fiber reinforced bridge decks. So, talk a little bit about fiber reinforced concrete as it applies to pavements and bridge decks, and then go into fiber reinforced concrete overlay design, a spreadsheet calculator we developed, and that calculator will also, hopefully in the next couple weeks, be on the CP Tech website that you can go use, and then talk about fiber reinforced bridge decks. And hopefully by the end of this presentation, you'll know a little bit more, unless you knew a lot already, about fiber reinforced concrete. You'll know something about the common fiber types. You'll know the primary test method that we typically want to use to determine the fiber dosage, but we're not going to specify exact dosages to use because it's very dependent on the actual project, the fiber type, and the concrete mix design. And there's not a single fiber that is the best fiber in the world to use for any and all projects. Again, it's project dependent. So just a little bit of background and a little pointing to some good literature to look at that gives broad overview of projects. Fiber reinforced concrete overlays, first used in Ohio in 1971 for a waste station, steel fibers. There's some good literature on using fibers in CRCP, mostly from Texas and Illinois. Also using fibers in roller compacted concrete. And then also using fibers for bonded concrete overlays. And finally, I don't think we touch on it really in this conference, but it's also been used in airfields. There are 4 fiber types. They're actually specified by ASTM C1116. The 2 most common types are steel and synthetic, or plastic. Glass fibers have been used in Illinois. I'm aware of several projects. One of the interesting things with glass is sometimes it does not arrive as individual fibers. There's actually a machine that as it discharges into the concrete truck, it chops a strand of fiberglass. There's also natural fibers, which are not as common. But the steel fibers must meet a separate ASTM standard, A820, and the plastic fibers or synthetic fibers, there's a whole wide range of plastic materials, but the only ones that are specified are polyolefin fibers, and that's in ASTM D7508. And polyolefin just is essentially anything that has ethylene or propylene in it. So polypropylene or polyethylene plastics, those are both olefins, and so that is a polyolefin type of fiber. In addition to the actual material of the fiber, there's 2 general types of fiber. You can have a macro fiber or a micro fiber. Macro fiber is typically a large fiber, anywhere from maybe 1.25 inches to 2 inches. Microfibers are smaller. The macrofibers are what gives you some additional structural capacity once the concrete has cracked. the microfibers really only help you with plastic shrinkage cracking control. The microfibers generally do not increase the structural capacity of your concrete. It just helps with that early age deformations. With both, we typically categorize the fiber with an aspect ratio, and almost all the fibers on the market are between 20 and 100, and that's just simply the length of the fiber divided by a diameter. Turns out through a lot of testing that if you're between that range, you'll get a good performing fiber. So let's talk about steel fibers. They're usually deformed, with the exception of maybe ultra high performance concrete, UHPC. We typically do not add straight, smooth fibers to concrete pavements. They usually are hooked or crimped. Something mechanical deforms it so that it has good mechanical bonding inside the concrete. And that ASTM A820 standard specifies that the steel used must have a minimum tensile strength of 50,000 psi. But there's a wide range of fiber geometries out there. I just showed two examples of hooked and crimped with steel fibers, and again, just mechanically deformed. The synthetic fibers, there's a lot more variation in the style of fiber that's out there on the market. You can have twisted, embossed, fibrillated. You're just trying to improve the mechanical and chemical bond of the fiber inside the concrete so that when the concrete does crack, the fiber just doesn't simply slip out. You want it to be bonded so it can provide some additional structural capacity. And just re-emphasizing, polyolefin just simply means ethylene and polypropylene or any blend of those. There are some fibers that are like 80% polypropylene and 20% polyethylene. They have different strengths and different affinities for water and bonding in the concrete. And speaking of bonding in the concrete, PVA, polyvinyl alcohol fibers, are by far the best that bond inside the concrete matrix. Sometimes they bond a little too well, though. But regardless of that, if I'm going to stick fibers into a concrete pavement overlay, the question I always get, and that the co-authors of this document always get, is, well, give me the dosage. I need to know how much fibers to stick into my mix. Well, you can't do that unless you know a few things about the concrete and where it's going to be placed and the expected traffic loading and all that. So we want to characterize the actual performance of the fiber and not just simply always say, okay, we're always going to add 4 pounds per cubic yard and call it good every single time. We want to look at how the specific fiber that we're choosing to use performs in our mixture. Some states do have prescriptive specifications on the books that just says flat out you must use 4 pounds per cubic yard or 3 pounds or some amount that is specified. It's possible that you could get a provision or exemption and choose a different amount, but it's in the specifications. And not to pick on Rhode Island, they have one of the most interesting specs in that you must have 50 million individual fibers per cubic yard of concrete. That's actually in their spec book. It says 50 million individual fibers. Not sure exactly how they came up with that and who's sitting there counting the number of fibers, but there's an interesting way to specify the dosage. More commonly, we specify it either by pounds per cubic yard or by a volumetric percentage. So with steel, because steel weighs more than plastic, to get the same volume, we typically add more, and we're in the range of 30 to 70 pounds per cubic yard for pavements. I know Missouri has done a bridge deck that went up to, I think, 80 or 90 pounds per cubic yard. So these are just general ranges. Synthetic, because they're lighter, to get the same volume replacement, we can get by with 3 to 8 pounds per cubic yard. A lot of times these fibers are added either at the batch plant or into the truck. Sometimes they're held together with dissolvable bands or in dissolvable bags. the state of Oregon actually does not allow you to toss the whole bag into the truck. You have to open the bag and dump it or not use a bag at all. A few other states have requirements on how to actually add the fibers into the mix. But regardless, these are the typical ranges of fibers we add for concrete pavements. But we need to determine the actual specific dosage for our project. There were two commonly used tests, the one shown here and then ASTM C1399. The ASTM C1399 is no longer in favor with ACI in terms of determining fiber reinforced performance of concrete. So the recommended procedure is ASTM C1609. And what this test is simply taking an MOR beam made of your fiber reinforced concrete, putting it in a much more complicated setup than this typical Forney 4-point test machine, and carefully loading the beam to capture the crack and then the behavior after the crack is formed, and you're continuing the opening of it. And so a typical output from this test is shown on the right. You have your peak load, and that peak load is directly your MOR value. So if you run this test, you can get your flex value with this test. You don't have to run a separate test. But then you're capturing the behavior after it's cracked and it's starting to open. A good fiber will maintain a high level of load capacity as it opens more and more. A poor fiber or an inadequate dosage of fibers will not maintain as much load carrying capacity in this test. And there are two specific points of interest that are outlined in the standard. There's one at, for MOR geometry, at 0.75 millimeters of deflection, and then at 3 millimeters of deflection. And you take the load values at those points, plug them into the equation in ASTM C1609, and it'll give you a residual capacity of that beam. So you get the peak capacity, the MOR, and then you get a residual capacity. You can also, in ASTM C1609, calculate that residual capacity as a percentage. However, that's also not really recommended because it's a percentage of your peak load. So if your peak load was 400 psi and the residual percentage was, let's say, 20%, which was commonly set as the minimum level of residual load, well, what's 20% of 400? It's a math question. 80 psi. But if my capacity, my tensile flexural strength of my beam is 800 psi, well, that same 20% is now a much higher number. So the percent does not give you a good indication of the actual capacity of the beam, because you can, if you just specify a certain percentage target, you could have a really low MOR or in just acceptable MOR and then inadequate load carrying capacity. So what is actually currently in certain specifications? Well, in Colorado, they set first a minimum amount of fibers you must use. You can go above it, but they say a minimum of 4 pounds per cubic yard, and you must have a residual strength of 170 psi when you run the 1609 test. So, if you find any type of fiber at whatever dosage above 4 pounds per cubic yard that meets this specification, they would consider it valid. Mississippi still uses the percent calculation from ASTM C1609, and they say your beam must have at least 20% residual load carrying capacity. So these are just two examples of about, I think it was 21 states that have specifications on the books regarding fiber reinforced concrete. But then what do you do with that number? How do you actually account for it in your design? Well, the proposed method is to simply take F1, which is your MOR value, your flexural strength value, and then add that 3 millimeter deflection value to it to get an effective MOR. Because the software out there right now does not really allow you to input that whole curve of your mixture. You just input an MOR value. So we're proposing, and it's been shown in the literature to be a valid method of taking that residual capacity at 3 millimeters of deflection, adding it to the MOR value, coming up with an effective value to plug into any one of these design software packages or other design software packages you're using. To help you know what residual capacity you're looking for, because 50 psi may not be enough, but maybe 300 psi residual capacity is too much. We've developed a spreadsheet calculator that will hopefully in the next couple of weeks be available on the CP Tech Center website, where you input your specific project parameters, like the type of overlay, the expected traffic level, the condition of your asphalt base, the expected design thickness of your concrete overlay, and it will give you a value that your target value you're looking for your composite or your effective flexural strength. So in this example that I realize is extremely hard to read on the screen, you basically started with 600 psi flexural strength. Given the example criteria set here, relatively low traffic level, fair asphalt condition, 3 to 4.5 inch concrete slab, it's telling you you need an additional 100 psi residual load carrying capacity in order to maintain adequate performance. And so it's telling you your effective MOR should be 700 psi. And that's the value you would plug into your design software. Now notice, this is not telling you what fiber dosage to use. It's just telling you whatever fiber dosage or fiber type you're using, it should hit at least 100 psi residual capacity according to ASTM C1609, or greater, you can be better, to meet this design criteria. As a more clear example of how this would be used, using the BCOA ME, if you have a design that's 4 million easels, moderate asphalt condition, you have 3-inch asphalt remaining, your overlay is between 4.5 to 6 inches, and you have relatively short joint spacing, and your target MOR is 600 psi. The BCOA ME with no fibers would tell you that the design for that overlay would be 5 3/4 inch thick. If you add fibers, and you add enough fibers to have 125 psi residual capacity, bumping your effective MOR to 725, the new design would be 4.5 inches thick. So you can take the effective MOR and plug it directly into whatever pavement design software you're using to get an estimate on how those fibers are affecting your actual design. Again, it's not telling you how many fibers. You have to run or contract out the lab testing to get these residual strength values for your fiber mix and your concrete mix. But once you have that, you can plug it into any of these design software packages. So in the document that's going to be published soon, there's a long Q&A section in the document, and I just put a few here that I thought maybe would be of interest to this audience. And one is, how do macrofibers affect contraction joints or construction joints? Well, if we're not, first of all, saying that you remove dowel bars. If your design calls for dowel bars, you should keep your dowel bars in. the fibers are not going to act in the capacity to replace dowel bars. However, it could potentially reduce or eliminate tie bars. However, if it's a construction joint and not a saw cut joint, you still need tie bars for this very reason right here. This was in Illinois. The slabs are migrating because they did not, there's a construction joint right here. They did not put tie bars. They just assumed that the fibers would hold the slab in place. And in fact, the slabs are migrating. It happens to be at an intersection, which is also probably the worst possible spot to have slab migration because you're stopping. You have a lot of lateral force being applied to these slabs. So, but if it's a saw cut joint, the fibers will sufficiently act as a tied joint, but not for construction because there's no fibers crossing that joint. Construction joint, you stop construction, then you recast later. So it can act like a tied joint, but not replace dowel bars. If you have construction, still need some tie bars. And by far the most common question, especially with steel fibers, and especially up here in the, well, I call it the north, where you have de-icing salts, will I have corrosion? Well, yeah, because you're throwing salt on steel, it's going to corrode. But turns out, and we see this in Chicago, because there's a lot of steel fiber reinforced pavements, that only the surface fibers corrode. And then they break off. They don't puncture tires or anything. They just corrode away. And then the interior fibers are generally non-corroded. Now, if it cracks a lot, yeah, the salts can really go in and start corrosion. But generally, it's only at the surface. If you're really interested in salt corrosion of steel fiber reinforced concrete, you can look up that reference. That reference only deals with steel fibers and corrosion of salt water and de-icing salts. Okay, bridge decks. I'm going really fast because there's a lot in the paper that's coming out, but also I want to keep us on time. So, made this map as part of this study, looking at what specifications exist out there with all 50 states in terms of fiber reinforced concrete as it applies to pavements and bridge decks. Well, and it turns out there are 3 states, Oregon, California, and Delaware, that require all bridge decks to have fiber reinforced concrete. The remaining colored states have various degrees of requirements for bridge decks in terms of fiber reinforcement. As some particular field studies, and there's more listed in the actual document, in 2000 in Virginia, 2 companion bridge decks were cast or constructed side by side, one with fibers and one without. And the dosage of the fibers was relatively high, 8.75 pounds per cubic yard of synthetic fibers. And after 5 years, the crack length in the fiber reinforced bridge deck had decreased 60% relative to no fibers, and the width of those cracks was 45% smaller compared to no fibers. In California, in 2007, only 3 pounds per cubic yard of synthetic fibers were added, but a relatively high dosage of a shrinkage-reducing admixture was also added. And after 5 years, there's almost no visible cracking in the deck. As a result of that study and several others in California, in late or early 2018, California issued a memorandum stating that all bridge decks must have a minimum fiber content of 3 pounds per cubic yard and a minimum SRA, or shrinkage-reducing admixture dosage, for all bridge decks constructed in California. In Illinois, there's a project, 3 pounds per cubic yard of synthetic fibers, no visible cracking after 1 week. This study was more looking at plastic shrinkage cracking, early age cracking of bridge decks, and they, in this study, successfully mitigated those. In 2017, they added 66 pounds of steel fibers, and an expansive compound, not necessarily a shrinkage-reducing admixture, as a calcium oxide-based expansive compound. And after 10 months, they only observed hairline cracking around embedded sensor trees. This was a smart bridge. It only cracked where they were sticking stuff in the concrete, nowhere else in the deck. And so fiber-reinforced bridge decks and pavements have been shown to have, at least within 5 years of service, good performance compared to not reinforcing it. And then there's one last project where the crazy Canadians decide, let's make a bridge deck with no rebar. So in 1995, in Canada, the Salmon River Bridge, they used 9 pounds per cubic yard of synthetic fibers, no reinforcing bars whatsoever in the deck. The entire deck was just fiber reinforced concrete. It was 8 inches thick, and they cast it. And I don't know if this is a sign of something went bad or not, but there's no other literature on this. They constructed it. You can go on Google Earth and do the street view on this bridge deck. It's now covered with asphalt, but I think it's the original deck underneath. I don't think it completely failed. But what they did, they wanted to see, could they simplify a construction process by not having to place rebar for a bridge deck? It seems like it worked, but do any of you want to risk doing that on a bridge deck with no rebar? I wouldn't, unless I wasn't going to be held liable. So anyway, tried to keep it quick. There's 2 documents that are coming out that have a lot more detail about this. The fiber reinforced overlays can definitely extend the performance and potentially reduce the design thickness from the get-go. But any specifications or any design that you're going to use should be performance-based, so following ASTM C1609, and not just prescriptive, like, oh, well, the fiber wait, are there fiber manufacturers back there? Okay. They don't do this. At least the fiber manufacturers I know don't do this. But don't just blindly use 4 pounds per cubic yard because that's what the spec says the minimum value is. I know the fiber manufacturers would be happy to sell you more fibers, but whatever dosage gives you the performance you're looking for is what you should use. And each mix and each project is different. Finally, that design tool should be available on the CP Tech Center website as a calculator that you can freely use in the coming weeks. We already submitted and got all the reports approved. I'm just waiting to hear back for that. And with that, I'll answer any questions or we'll go on to the next speaker.